Now here's something with the stopping voltage. Remember that the energy associated with the stopping voltage, remember that energy can be expressed as E delta V in electron volts, all right? And so the energy associated with the stopping voltage in electron volts is E times whatever that voltage is. And it is just stopping the photons with the maximum kinetic energy. So guess what? You can calculate the maximum kinetic energy of the photoelectrons by conducting this experiment and seeing where the current stops, right? Because when you stop having a current, by increasing this more and more negatively, suddenly the current goes down, 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 and eventually it stops. Look at that voltage. That's the stopping voltage. E delta V equals the energy required to stop the most energetic electrons, photoelectrons that were coming from over here. That's important. So this over here is E delta V. You can read that off of the voltmeter. That equals the maximum kinetic energy of the electrons. And the nice thing is, if you write, you're going to write all of our energies in electron volts. And so whatever that voltage is, let's just say it's whatever 3 volts. Then 3 electron volts, so 3 volts stopping energy means that if you put it in terms of energy, it's 3 electron volts, eV. And that's the maximum kinetic energy of the photoelectrons, it's 3 electron volts. Whatever that number is off the voltmeter, put an E in front of it, you turn it into an energy, 3 electron volts, because that was 3 volts, and that's the maximum kinetic energy of the photoelectrons. That works out rather nicely. Now, there's a lot of peculiar things about this. You absolutely should read 2 different things on page 878 and 879. Page 878 at the bottom, all right? Get out the textbook and read this part where it says several features of the photoelectric effect cannot be explained by classical physics or with the wave theory of light. Read that. It's important. Read that and make notes about it, all right? Write those things down in your notebook and reread them and know that, okay? And then the other part, we're not quite ready for this yet, but that's they have bullet points on page 879 towards just below the halfway point. You're going to want to know those too, where it says photoelectric effect that cannot be understood using concepts of classical physics, and they have a list of those things. You're going to want to know those. The big secret here that you want to just digest is what they ended up realizing is that it's a 1 photon for 1 electron exchange. It's a 1-for-1 exchange. Here's what classical physics wave theory would predict. You would predict that as the wavelengths come in, the wavelengths of light, all right, as the waves come in, eventually enough energy, because there's energy in this thing, all right, as enough energy comes in, and as enough waves come in, then the electrons, any light would do, as long as you're patient, and you can make it like increase the intensity, increase the amplitude, and eventually, any light would work, low frequency, high frequency, and the electrons would absorb that electromagnetic energy from the wave and then eventually be kicked off. That is not what happens. It's not what happens at all. Instead, what they're finally able to conclude is that it's not a question of waiting for enough energy from the wavelengths of light to appear. The electron absorbs the energy from 1 photon and 1 photon only in order to kick it off. So that that single photon has to have enough energy, all right? That single photon has to have enough energy from that equation to provide that to make it across this space, all right? To kick it off of the metal and make it off that space. Well, some metals don't allow that. You shine a certain kind of light on it, you calculate the energy, it's not enough energy to kick it off of the metal, all right? Again, it's per photon. It's per photon. Let me restate that because it's so important. The amount of energy is based on 1 photon for 1 electron. That's it. That's why, if classical theory were correct, that would not be the case. You could just shine and be patient and wait for enough energy to come from the waves. That's not what happens. The other thing that's interesting, they talk about this in the textbook, is that you should, so let's say we're just waiting for an entire wavelength to arrive. Well, you'd have to wait for the entire period of the wave to get there before you've absorbed the entire wavelength, all the energy associated with that, to kick off an electron. And that's not what happens. It all happens essentially instantaneously, like all the energy is right at the leading edge, all of it. You don't have to wait for all of that. It all comes at the very beginning of the wave. All right? So particles, wave is a particle traveling in little packets, all condensed, all quantized in a little packet, a little bundle of energy. It all arrives at once. You don't wait for the entire duration of the wave length, for the period, to get here. It all arrives in packets. That obviously cannot be explained by wave theory. It can only be explained if light is a particle. Okay, so you've got a couple of equations. You know the energy of a photon of light coming in is that. You know the maximum kinetic energy of the photoelectrons is that. This is the stopping voltage, all right? Again, energy of a photon, that's the maximum kinetic energy of the electron. By the way, you know that energy equals HF. You also know that F equals C over lambda. And actually, more often than not, we talk about wavelengths instead of frequencies. So this can be written as E equals HC all over lambda. Okay. There is something that you definitely want to take a look at on the equation sheet. Not the equation sheet, the table of information. And that is just underneath Planck's constant is this value. It's important to know this. They've actually done the math for you, and it's on here. Okay, remember you get this for the multiple choice as well as the free response. They've done the math. They've multiplied h times the speed of light in the vacuum. And they have it in SI units, which is joule meters, all right, and that's 1.99 times 10 to the negative 25 joule meters. That's great, but we normally deal in electron volts and nanometers when we're talking about light. And that's the number you're going to want to remember. So HC is 1240 electron volt nanometers. So when we are dealing with electron volts, that's 1240, the entire numerator. Your wavelengths will remain in nanometers. Do not convert them to meters because this is based on nanometers and electron volts. Your energies will be in electron volts. So one more time, when we get into this, your energy, electron volts, okay? HC, that's 1240 electron volt nanometers. And then lambda is going to be in nanometers, okay? And then your frequency is still going to end up being in hertz. We'll talk about that in a little bit. All right. So, one other basic. Well, I'm about to run out of time. Hold on. I'm going to start this again. Just pause.